Okay, well, welcome newcomers and regulars. This is the RIOT Science Club, Wolverhampton. I'm Sam Westwood, the co-lead alongside Ian Lahart, who's in the background helping produce today. For those who don't know, we're a mainly early career researcher-led initiative, and we host weekly seminars where we discuss all things regards reproducibility, openness, transparency in science and research generally, and scholarship. All of our content can be found in various places. Check out our website, www.riotscienceclub.co.uk, and of course, all of our previous talks are uploaded to our YouTube channel, and you can also see us on Twitter as well at RIOT Science Club. Today we are joined by Stephen Senn, and I've got some notes here because Stephen Senn, it's either he needs no introduction or you have to condense quite a prolific career in a short space of time, so I'll do my best. So Stephen is a world-renowned statistician, and is noted for his contributions in statistical analysis in medicine, both in terms of teaching and in research practice. He earned his PhD in statistics at the University of Dundee and at Dundee College of Technology, now the Abertay Dundee. He was a lecturer also at UCL and Glasgow, and then he went on to heading the Competence Centre for Methodology, and he's a statistical consultant. He's written several books, including Dicing with Death and Statistical Issues. Oh, my notes have been smudged here. In Crossover Trials. And he's also done several rounds on the television. You might have seen him from University Challenge, where he represented Exeter, and in my view, robbed when he did his turn to represent the Royal Statistics Society. Stephen is very well known in the open science and reproducibility community, and he's helped in a capacity on the advisory board for the Swiss Reproducibility Network, which is a sister to the UK Reproducibility Network, and we're very glad to see that initiative expanding globally. So, Stephen, I'm going to put you on camera now and hand the keys over to you. So thank you very much for agreeing to give a talk today, and the floor is yours.
Okay, thanks very much. Just checking, can you see me advance a slide like that?
Yes,
yeah,
perfect.
So first of all, thanks to Ian for the invitation. And just to say that part of this arose out of work that I was doing when I was based in Luxembourg as a project that was looking at methods that could be used for rare diseases. So basically with small samples, and so the thing is fairly relevant. Can you still see me? Nice.
Yes, yep.
Some reason, okay. So what anybody does when they want to cover up for the fact that they've made some pretentious promises regarding what they could talk about, I went and had a look at Wikipedia to see what exactly are the coherence and the correspondence theories of truth. It's a long time since I looked at these. And it tells you that the coherence theory of truth is essentially to do with not issuing contradictions, making sure that things that you say are internally consistent. And interestingly enough, it highlights, or I have highlighted, a link it gives you to Bayesian epistemology. So the Bayesian method, or at least one particular approach to Bayesian inference, seems to be very much in line with this coherence theory of truth. But there's another theory of truth, the correspondence theory of truth, particularly associated with the name of Tarski, which essentially says what seems to be a very, very innocuous and rather stupid and elementary point, that basically things are true if they correspond, statements are true if they correspond to a state of nature, which is true. I'll come back to that. So this is what I'm going to talk about. I'm going to talk about some recent criticisms of p-values, significance tests, hypothesis tests, and all of this. And if you were to have a look at the talk that there has been, the various papers that there have been, the blogs that there have been on replication crisis, so-called, you'll find that p-values are pretty much regarded as being the villain in the piece. I'm going to talk about Replicate. Some of you may know about this, about the work of Ionides, about David Cahoon's work, about the American Statistical Association statement about p-values and about a proposal by Benjamin et al. As to how we should run significance tests in future. I'm then going to give you a brief history of p-values and explain really why p-values are so controversial, at least why I think they are, and then basically say whether or not I think that Bayes is a good thing, whether it will actually help the replication crisis, and want to persuade you that in actual fact just becoming Bayesian won't solve the problem, and give you some conclusions. So just a background explanation. I worked for over 30 years on statistical problems in drug development, and I tend to think of everything in terms of pharmaceutical trials. And there are two things you should know. One is that whether or not trials are run one-sided or two-sided, whether or not your objective is simply to prove that two treatments are different or to prove that one is better than the other, then in that case, the FDA always requires you to have two-sided tests 5%. So basically, since we often want to prove that the new treatment is better than the existing one, we're effectively running, from one point of view, 2.5% tests one-sided. The other thing is that if you go to phase 3, you're expected to come with 2 significant results, not 1. So here are some recent criticisms. Here's a summary in Science of a particular food fight, as they called it, how it was going on, why it was going on. In countless tweets, the replication police were described as shameless little bullies, self-righteous, self-appointed sheriffs, engaged in a process clearly not designed to find truth, second stringers who were incapable of making novel contributions of their own to literature, and most succinctly as assholes. So you can see that this is America and not Great Britain, which is being talked about. But actually in Europe recently, there's been a row about the poor reproducibility of certain trials of substances used in COVID. I'm not going to name the substances, nor name the authors, nor name the trials, but it's even got so far as to legal action being threatened for people who claim that the results are rubbish. So here is the Many Labs replication project, a very energetic project run by a number of psychologists who agreed that they would try and reproduce some key experiments in psychology, some key findings themselves in various labs. And this is a sort of particular scatter plot which is supposed to show the original finding that they were trying to replicate as an X on this particular plot, and the replications which are given by various circles. And obviously there's a distinction between American results, which presumably are regarded as being particularly trustworthy, and international ones as less so. And so what they have done is they have made a symbol difference between the two. US is a filled circle, international is an open circle. And you can also see the meta-analysis for the various results. Now, when I saw this, I thought, crikey, the psychologists actually do work that can be replicated, which shows what a cynic I am. I actually thought that nearly everything in social psychology was utter rot. And I was astonished at how well everything held up. But those who were working in social psychology were disturbed. They thought that everything that they did must be true, and therefore the fact that not everything was replicated must be some sort of a scandal. I'll come back to that also. This is the work of Ioannidis, a paper that has received nearly 10,000 citations by now. And he does a sort of simple Bayesian analysis in which he supposes that there's a ratio of true alternatives to true null hypotheses, which he calls R. That leads to the particular probabilities shown on this diagram, R over 1 plus R, or 1 over 1 plus R, for the alternative or the null hypothesis being true. And he then supposes that we're going to run out of tests, have a test with a particular type of error rate alpha, and that it might have a particular power, 1 minus beta, and then we actually get a positive result. What can we say about whether this positive result was a true positive result or not? Well, we simply need to take this probability tree and then eliminate the cases that don't apply. Those are the cases that correspond to a that correspond to a negative result. Those have been eliminated because we actually had a positive result. And then the question is, what is the probability that the positive result came from an alternative hypothesis rather than a null hypothesis? And a simple application of Bayes' theorem gives you the answer. And the true positive rate is given by the expression on the left-hand side. Well, that's a bit difficult to see what's going on, but here's a diagram which shows what the true positive rate is according to the value of R that is chosen. The value of R equals 1 means that null and alternative hypotheses are equally likely, and these three particular curves gives you the true positive rate as a result. And a particular finding that Ioannidis has, which was not new, is well known, was that the higher your power, the more likely a significant result is to lead to a true positive rate. And low power had long been identified as being a problem in experimentation. David Cahoon has also been, in recent years, a very firm critic of significance testing. And this is what he has to say. One must admit, however reluctantly, that despite the huge contributions that Ronald Fisher made to statistics, there is an element of truth in the conclusion of a perspicacious journalist, and here he cites Robert Matthews. The plain fact is that 70 years ago, Ronald Fisher gave scientists a mathematical machine for turning baloney into breakthroughs and flukes into funding. And this is published quite a long time ago, and in all places, the Sunday Telegraph. So you might say that if something like this hits the Sunday Telegraph, then in that case, it surely ought to be very widely known amongst the scientific community. And David then goes on to give a recommendation. If you want to avoid making a fool of yourself very often, do not regard anything greater than p less than 0.001 as a demonstration that you discovered something. So what he's looking for is a much, much more stringent standard. Here we have the ASA statement of 2016, and a number of statisticians were consulted about this. I was one of them. We had great difficulty in finding something we could all agree on, but perhaps the most important one is the last one. By itself, a p-value does not provide a good measure of evidence regarding a model or hypothesis. This is something of a scandal, perhaps. And then here we have a more recent proposal by Benjamin et al. They don't go quite as far as David Cahoon, but they are proposing that the common standard of significance, p less than 0.05, be dropped to p less than 0.005. And this particular paper has already received more than 1,500 citations. So in summary, what we can say is that many people claim we've had a replication crisis, and p-values, significance tests, the standard way of judging whether something is worth looking at or not, has come under fire. Significance is given far too easily. And there's a lot of advice, but it's not necessarily in agreement with, not everybody is in agreement with each other. But one of the things I find strange is that nobody actually seems to consider what we want from replication. What are we looking for? So I'm going to give you a brief history of p-values in order to show that the situation is rather odd. So this is a common story, and the villain of this story is R.A. Fisher. So scientists were treading the path of Bayesian reason. So back in the 18th century, Thomas Bayes and then Pierre Laplace had discovered the particular Bayesian argument, and they'd been using it for well over 100 years. And along came R.A. Fisher, and he persuaded them into a path of p-value madness. And this particular use of p-values, all the fault of R.A. Fisher, is responsible for a lot of unrepeatable nonsense. Now, if only we could wind back the clock and we could get people back onto the path of Bayesian virtue, then in that case, everything would be okay. But in fact, this history is false. It wasn't like this at all. And you need to understand what the history was in order to see the problem. So let's go back to Student's famous paper of 1908. At the top of this slide, you'll see a quote from that. And he analyzes some data. And he says from the table, the probability is 0.9985. This is from the table that he himself had laboriously produced for the T statistic. Or the odds are about 666 to 1 that 2 is the better seriffic. He fails to note the evil significance of 666, the number of the beast here. But nevertheless, what he's doing is he's calculating a Bayesian probability. If you look at R.A. Fisher, looking at the very same problem, he says for n equals 9, only one value in 100 will succeed 3.25 by chance. So the difference between the results is clearly significant. So student gives an interpretation in terms of the probability of a particular hypothesis being true, and Fisher gives the interpretation in terms of a result as extreme or more extreme if the hypothesis is true. This is a representation of how student sees it. This is the posterior distribution using his own theory that he developed, and he's looking at the difference in hours of sleep between two optical isomers, or so he thinks anyway, in inmates of the mental asylum at Kalamazoo to see whether this was whether there was any difference in these two as regards inducing sleep. And he finds a particular mean difference, and he then calculates the probability for the true parameter value based on the statistics. In other words, he's constructing a Bayesian argument. And you can see that what we might call the null hypothesis is way to the left, and that's how he gets this particularly impressive odds that there must be something in it. There must actually be a difference between the two isomers. Fisher looks at it a different way. He says, well, let's assume that the null hypothesis is true, that there's no difference between the isomers, and now let's calculate how probable it is that we would see a particular difference out as far as this. In actual fact, what he does is he quotes the 1% value, and he notes that the mean difference is beyond that rather than actually calculating the probability. But had he calculated the probability, he would have come to exactly the same probability as student. The difference is not in the probability, the difference is in the interpretation. So these are the two interpretations together. The distributions are different, but one is a reflection of the other. And essentially, it's following on from the sort of work that Laplace had, assuming an uninformative prior, that you can turn the data distribution, which is essentially what Fisher is using, into the posterior distribution, which is essentially what student is using. But the important point to note here is they're not going to come up with a different numerical value. And since they're not going to come up with a different numerical value, it's rather baffling as to how you can blame Fisher for having promoted p-values for being responsible for the particular wrong interpretation that there is regarding the results that you get from significance tests. So I think I'm going to skip over this and just point out to you that numerically, basically, Fisher and student would agree. If they'd had modern resources, they could have calculated like this. They're supposedly comparing two particular optical isomers. The p-value, the probability one-sided is 0.0014, which a student converts immediately into an odds that the null hypothesis is, or the alternative hypothesis rather, is true. Whereas Fisher could have calculated the two-sided p-value, which is 0.0028, which is simply twice the value that student has for the tail area. So the only innovation, if anything, is a suggestion from Fisher that maybe one should use two-sided value, but he can hardly be accused, if that's the case, of trying to make things more significant, to use the modern word, than they really are. If anything, the reverse is the case. So why do some modern Bayesians think p-values overstate the case against H0? Well, the answer is to do with Harold Jeffreys, so let's have a look at him. And this is basically from Jeffreys' book, his Theory of Probability, and he was particularly impressed by a Cambridge philosopher called Broad. And what Broad had realized was that there was a problem with Laplace's approach to Bayesian inference. And the problem was that even a large number of successful results could not render a scientific hypothesis probably true. And Jeffreys regarded probability as being the right way to have a look at truth or otherwise of scientific hypotheses. And for this, it was absolutely intolerable that this was the case, but he recognized that Broad had a point. And the solution he came up with basically was to say, well, it's because the problem is in the particular prior distribution that Laplace has used. We'll come back to that. So this is Broad. He graduated Cambridge in 1910. And so he was just a little bit older than Jeffreys and Fisher. Returned to Cambridge in 1926, and he was interested in epistemology. And the irony is that really, as regards epistemology, he was really a pretty severe cynic. He rather doubted that many scientific laws could be true. But perhaps despite this, or maybe because, I don't know, he was actually interested in psychic research. So he was reasonably impressed by some of the psychics that were around that were claiming to have results that were rather impressive in the early part of the 20th century. And what Broad showed was that if you want to show in a particular sampling problem, if you want to answer the question, is it the case that all of the counters in a particular bag are white? I'm not allowed to draw them all, but I've drawn a large number so far. Then the answer depends on how many counters there still are to draw. And if there are still more white counters to draw than you have already drawn, if you had a completely uninformative prior, then the probability is less than 1/2 at this particular stage that all the counters in the bag are white. The probability that most of the counters in the bag are white may well be quite high, but the probability that they're all white is still low. And all white is the sort of thing that corresponds roughly to a scientific law. So this sort of finding was intolerable to Jeffreys. And so the way that Jeffreys solved this was by placing a solid lump of probability on a null hypothesis is true. And basically, I suppose he had some sort of belief or some sort of rationale that one should act as if, other things being equal, simpler hypotheses are more likely. So you should simply give the benefit of the doubt to the simpler hypothesis by placing a lump of probability on it. So the real history is as follows. Scientists before Fisher were using Taylor probabilities to calculate posterior probabilities. This was following Laplace's use of uninformative prior distributions. They did also, by the way, occasionally use p-value logic. Carl Pearson occasionally described things in terms of p-values, but he was basically a Bayesian. And Jeffreys, influenced by Broad's criticism, was unsatisfied and used a lump prior. In fact, Etz and wagon makers have claimed that Haldane was there before Jeffreys and did it as early as 1932, but in fact, Jeffreys together with Rinch had already published articles suggesting this was a good thing. So it's Bayesian Jeffreys versus Bayesian Laplace that makes the dramatic difference, not frequentist Fisher versus Bayesian Laplace. This is one of the things which rather irritates me when people say, well, you should be a Bayesian rather than being a frequentist if you want to solve this problem. What I would like to know is, what exactly does it mean when you say you want to be a Bayesian? What sort of Bayesian do you want to be? You can simulate this sort of thing, by the way. I've simulated the empirical false positive rate versus the p-value here. What I've done is I've assumed in one case that we have a smooth prior. Essentially, I'm using dividing hypothesis. And in the other case, I've allowed for a lump of probability like Jeffreys. And you can see that the false positive rate is dramatically different depending upon which side sort of a Bayesian you are. The blue line is sort of post-Jeffreys, and the red line is something to do with Laplace. And Laplace does not, in fact, contradict the usual p-value idea, even though they should be interpreted differently. But I mean, it doesn't numerically contradict. Why the difference? Well, imagine a point estimate of 2 standard errors for a large sample. Now consider the likelihood ratio for a given value of the parameter delta under the alternative. If it is the case that the value at 0 is itself not particularly likely, then you're going to have difficulty finding support for the value at 0. But if what you can do is you can place a huge lump of probability at 0, which is what Jeffreys would do, then you have essentially an inexhaustible jar. For any particular possible value under the alternative hypothesis for delta, the true difference, you can compare it to the value at 0, which is under the null hypothesis. You're never going to run out of these possible values at 0 that you can repair it to, because you have a lump of probability there. And if you have a look at the red curve, you will see that as it stretches out to the right, and it stretches out to the right towards infinity, eventually some of the values under the alternative hypothesis are less well supported than they are under the null hypothesis. This never happens unless you have some sort of a concentration of probability near zero. So in summary, the major disagreement is not between p-values and Bayes using informative prior distributions, it's between two Bayesian approaches, one using uninformative prior distributions and the other one using a highly informative one. The conflict is not going to go away by banning p-values, and there's no automatic Bayesianism. And by the way, I work in drug development, and if you are comparing two particular drugs, only by a miracle could they be literally equivalent in terms of efficacy if one of them is already proven to be efficacious. That miracle would require that the new treatment was also efficacious, and you happen to have chosen the dose of the new treatment that just happened to be equipotent to the standard one. So it's far from obvious that just in a brain dead way, assuming that every time you happen to compare two things, you should be assuming a huge lump of prior probability on exact equivalence is a good thing to be doing. So why Bayes won't solve the replication crisis? By the way, it's not just frequentists who are skeptical of a lump at zero. These are the various commentaries that there were on the ASA statement. You'll find me down there somewhere. And I decided, just out of amusement, from the various statements to try and classify people according to two axes. One axis is whether they were frequentist or Bayesian, and the other axis is whether they were interested in dividing hypotheses essentially in estimation problems, or whether they were more interested in testing problems. And it's really the people who are up on the left-hand side, on the right-hand side, the northeast corner, if you like, of this particular diagram, assuming that I've got my directions straight, Benjamin, Berger, and Johnson, who have most problem with p-values. They are essentially following the Jeffreys program, and they regard it as being extremely important that you should be able to have these cases where there's a lump of probability on zero. I think we can skip that slide. Let me show you the sort of thing that we might have. This is an adaptation from Ioannidis, and here I show you what would happen if we were to go over to the Benjamin et al. Proposal. Remember that they were proposing that we drop the standard alpha level. What have I done here? I've got this wrong. That red one down there should be, one of them should be 0.05. I don't quite know how I managed to do that, but anyway, there we are. The labels are wrong, but basically the situation here in this particular curve is that if what you do, set of curves is that if what you do was you were to drop the significance level, the standard significance level from 0.05 to 0.005, then in that case there would be virtually no effect as regards the true negative rate, but in actual fact you would have a considerable difference regarding the false positive rate. I'm going to move on to that and hope that this particular diagram shows it somewhat better. Yes, it does. However, there's a problem here. There's something rather unfair about the previous diagram. If you look at the previous diagram, essentially to compare like with like, one has the tendency to compare points with the same power. That's what I've done. But in actual fact, if you have a fixed amount of resources available, if what you do is you drop your type 1 error rate, you will have to drop your power. And so this particular diagram shows what would happen if we use the value of r equal to 1 that Ioannidis has considered, and we had the same resources available. Your power would drop from 80% to 46.4%. And if that's the case, you will actually end up with an overall lower correct decision rate by using the Benjamin et al. Rule. If you consider that false negatives are also a problem along with false positives, then in that case, this particular proposal could be harmful. I say could because it would depend on the value of r, and it may well be that a value of r equals 1 is too optimistic. That effectively corresponds to half of all alternative hypotheses being true. That might be reasonable in my field coming out of phase 2, where you've already studied quite a lot of treatments and you're now going to test them for phase 3. One might say that even there, that the value of R is not is not high enough, that we have a higher feeling that that the new treatments will be effective. But you can see that you won't necessarily end up having more correct statements if this is what you do, because you will increase the false negative rate. Well, you might say, well, I don't care about false negatives. Well, then I have a proposal for you. If you don't care about false negatives, simply never, ever, ever declare any null hypothesis as being rejected. Then in that case, you will never have anything to worry about. As soon as you admit that false negatives do have a cost, then we're into the hypothesis significance testing or even Bayesian testing approach. So that particular excuse is not an excuse. You have to think about the false negatives as well as the false positives. This, by the way, is what happens if you use David Cahoon's rule. This would be even more disastrous, provided, of course, that the value of R equals 1 is true. I'm not saying that there are no values of R where it might not be a good rule, but it's certainly not a good rule for the fixed resources that you've got if you care about false negatives. So I'm going to give you a quote from R.A. Fisher here, which is rather important. A man who rejects a hypothesis provisionally as a matter of habitual practice when the significance level is at 1% will certainly be mistaken in not more than 1% of such decisions. For when the hypothesis is correct, he will be mistaken in just 1% of these cases, and when it is incorrect, he will never be mistaken in rejection. So the critics of significance tests are right in saying one should not lazily invert the p-value and assume that it gives you the probability of the null hypothesis being true. Low p-value equals low probability of null hypothesis being true. That's a lazy habit. Nevertheless, what significance tests claim to deliver is still true. You will rarely be in the position of having a p-value between 5% and 0.5%, the value that Benjamin et al. Want to propose, when you run tests. Because either, as Fisher points out, the null hypothesis will be true, in which case, for that particular example, only 4.5% of all particular trials run would end you up in that particular situation, or the alternative hypothesis would be correct, in which case, whenever you came to that conclusion, you'd be making a correct decision. So this cannot of itself be the explanation of a replication crisis if there is a replication crisis. Note, I'm not claiming here that there's no case for making the significance level lower. There may well be, but that has to be argued very, very carefully, depending upon the context and depending upon the cost of false positives and false negatives. Now, I'm not arguing against that necessarily. However, to say that the replication crisis is caused by p-values is simply balmy. If there is a huge replication crisis, it cannot be caused by this particular approach. And I myself would label something else as being a more plausible villain, and that is that people get their standard errors habitually wrong, especially when it comes to observational studies. But in actual fact, the standard errors that are being quoted for studies are far too low. The true standard errors are much, much larger. So here are some conclusions. For given resources, your overall decision making may actually be worse if you lower the threshold for significance. Only if false negatives are negligible cost is this sensible. Lax standards cannot be the explanation for most results being false, since very few null studies will end with a false conclusion. If you want to find out the truth, then requiring a single study to deliver it may be a bad strategy. And this is, of course, the strategy in drug development, where essentially decisions are made upon a number of studies. By the way, there's a lesson here for meta-analysts. If you are replacing 2 significant results at phase 3 by a meta-analysis, then in that case, 5% is quite the wrong standard to be using. 2 results equivalent. 2 results significant at 5% do not correspond to 1 meta-analysis significant at 5%. The meta-analysis is a much, much lower standard. So if I've got a bit of time still, another criticism being made of p-values is that they're inherently misleading because what people don't understand is that the probability of repeating a result that is just significant at the 5% level, p equals 0.05, is in fact only 50%. Isn't that a scandal? You have in fact got a result which is just significant, let's say p equals 0.049. You carry out the trial again. What's the chance that the new trial will actually confirm or replicate the result you had before? Well, here are 3 possible questions we might be interested in. Question 1, what's the probability that in a future experiment, taking that experiment result alone, the estimate for B would after all be worse than that for A? So this is just a sign reversal of the actual estimate, so it's a very weak standard of replication. What's the probability, having conducted this experiment and pooled its result with the current one, we would show that the estimate for B was after all worse than that for A? So what's the result that the cumulating evidence, including the study already run, would be worse than that for A? And question 3, which is closer at least to the question that Goodman is posing, and which we could also pose in a Bayesian form, which I'm posing here. What is the probability that having conducted a future experiment and then calculated a Bayesian posterior using a uniform prior and the results from the second experiment alone, the probability that B would be worse than A would be less than or equal to 0.05. So essentially, what's the probability of the replication of the Bayesian probability we had previously from the first trial? And this particular slide shows the situation. The x-axis gives the ratio of the standard error from the first experiment to the second. So the value of 1 in the middle of that particular diagram, note the logarithmic scale on the x-axis, the value of 1 corresponds to the new trial, the second study, being exactly the same as the previous trial, and you will see the dashed blue curve, which is this sort of common replication event that everybody looks at. What's my chances of getting the same result in terms of significance or in terms of Bayesian posterior probability just using the trial on its own I had before? You will see that that probability is indeed 0.5, sorry. But if, however, the ratio of the first standard error to the second arises, which is to say if the second trial was much, much larger, then in that case that rises to nearly 0.975. And this is one of the points of my particular talk here. We shouldn't be looking at the probability that another study replicates the study we've already run. That's some sort of weak coherence requirement. We should be looking for a correspondence requirement. We should be looking for the probability that the result that we have actually corresponds to the truth. And that means, to what extent would it predict the value from an infinitely large experiment to follow, not an experiment of the same size? And that particular probability is not itself worse for p-values than for Bayesian analyses, unless you are able to use prior information as to what the likely value is of the true result. That knowledge alone is what could enable you to escape this particular diagram I've produced here. So I claim in a piece I wrote about Steve Goodman's very interesting paper, by the way, I claimed the following: it would be absurd if our inferences about the world, having just completed a clinical trial, were necessarily dependent on assuming the following. We're now going to repeat the experiment. We're going to repeat it only once. It must be exactly the same size as the experiment we've just run. The inferential meaning of the experiment we've just run is the extent to which it predicts this second experiment. It's not prediction of the second experiment which is important, it's prediction of the truth which is important. In short, if you have two trials of equal size and nothing else is known, then for any statistic, it doesn't matter what statistic it is, the probability that is higher in A is the same as it is higher in B. This is true for any statistic, not just p-values. The probability that the statistic you've chosen is more impressive in the second trial or the first trial is just the same whichever way around you look at it, provided you have no further information. If you have further information that can somehow show you that the result from one of the trials is unusual, then you can know which way to bet. So what we need to consider is the infinitely large experiment, and this is exactly what the correspondence theory of truth requires. Now consider the many labs project again. Let's go back to it.
Stephen, sorry to interrupt whilst you're mid-burst. I think there's a slight pixelation issue with your slides. It seems to be that they keep... right, okay. Now, if you just go back onto the slideshow.
Yeah.
And... Perfect. Okay, yes. It was just that it seemed that as you were advancing, there was sort of residuals from the previous slide sort of dotted around.
Sorry about that.
Okay.
I don't know why it was happening. I was having difficulty advancing it anyway. So I apologize.
Okay, so it's all clear now. But maybe if I could ask, if you just go back a slide so that there is a sort of okay, that's fine. It was just that one was a little bit missed. The immediately preceding slide. So yes, sorry, carry on to the where you left off. Thank you.
Can you see the many labs replication project now?
Yeah.
So the thing about this particular diagram is that the way, in my opinion, unless I'm misunderstanding it, the way in which we should judge this particular remarkable effort, I think, I mean, this is a really praiseworthy effort to go to all of this to do this, and extremely interesting, is to judge the replication by the meta-analysis. And here I find results that are absolutely astonishing. What we have is really studies which seem to hold up incredibly well. The anchoring studies towards the top seem to hold up particularly well. It's true that we have two studies that don't hold up, the flag priming and the currency priming studies. But I would say that this is actually rather a good rate. I don't find this particular result shocking. And as I say, if anything, well, in particular, my respect, my sort of admiration for social psychology rose no end as a result of this particular study, not only because of the work that the people had gone to, but the fact that they found things that really held up and were important. I've been far too cynical myself. So have my slides advanced okay now?
Yes, it's working.
I'm on to the conclusion.
Yeah.
Right. Okay. So this is what you should know. P equals 0.05 is a weak standard of evidence. Requiring two trials is a good idea. And to pick up on something I said earlier, if you replace them by a single larger trial or a meta-analysis, ask for P equal 1/800. Variation in results from trial to trial is natural. Don't just rely on p-values, pay attention to the ASA advice. Failure to replicate is part of science. I work in a field where this is taken as being self-evident. You go through lots and lots of phases and preclinical work as well in drug development to establish that something eventually works to your satisfaction, and there are many disappointments on the way. We do need to deal with data dredging, publication bias, and probably I should really add pseudo replication to that. There is a big problem with standard errors, in my opinion. Bayesian analysis can be excellent, and in fact I do some myself from time to time, but I also think it's harder than many people think, and I have a suspicion of automatic Bayesian approaches. And I'd like to finish finally with this very nice quote from a very nice piece by Gigerenzer and Marevsky. Proponents of the Bayesian revolution should be wary of chasing yet another chimera, an apparently universal inference procedure. A better path would be to promote both an understanding of the various devices in the statistical toolbox and informed judgment to select among those. And here are some references. Thank you.
Wonderful. Thank you so much, Stephen. I'm going to leave you and the slides on the screen. So I will now just move on to reading the questions aloud to you that have appeared in the chat. For those people who have not asked a question yet, please do feel free to use the chat, the Q&A function, I should say, and we can try to deliver those to Stephen before the hour is up. We have a few questions and comments from a Mr. D. Colhoun, who's joined us. So your starter for 10. I tell you what, they've come in as you've been speaking. So these are sort of out of time, I guess, with well, I'll just read them aloud in the order they came in. So David says that a problem with the tree approach is that it understates the false positive risk because it implies P less than rather than P equal approach. I don't know whether you want to comment on that.
Yes, I agree with that. And it's a point that I've made myself in various publications. But that's not actually relevant when one has a look at claims that there is a huge problem with replication because of using that particular standard of 5%. Because to do that, you have to go back and do the sort of calculations that I was doing. And I don't actually think that David has done that. I don't think that David has actually gone so far as to work out what the predictive consequence is of the particular claim. To claim that that would be a reason, I mean, this cuts both ways. To claim that would be a reason for poor replication, one would have to show that a large number, there will be a huge number of results in the range. Let's say, to take David's standard, 0.001, 0.05. And that's simply not possible. You cannot get a huge number of results in that particular range. That's not an argument against making the results tighter, because by making the results tighter, then in that case, if there aren't going to be many results in that particular range, you might say, well, you know, what are we losing? But to do that calculation properly, you have to consider the resources available, and you have to go through everything. You have to go through conditioning on the resources available and thinking also what the cost of false negatives is, and so on and so forth. But yes, in a sense, if you actually observe P equals 0.049, then that's more problematic. But that's not quite relevant to the replication crisis itself.
Okay, another comment by David is, of course, false negatives matter. I would interpret my FPR approach as meaning that science is harder than we thought. You can comment on that, or I could move on to the next one.
Well, okay, I mean, all I can say is maybe. It's not clear to me what we should be doing then in that case. Should we, in fact, you know, what is your argument then in that case, David, for not dropping the standard by a further factor of 10, or a further factor of 10 after that, or, you know, any factor? Unless we do the calculation taking into account the false negative, there's no point in not continually reducing the standard further and further and further and further. So they simply cannot avoid the false negative problem. It's analogous to saying I've got a test for COVID. The specificity is brilliant. What's the sensitivity like? I haven't got a foggiest clue.
Right. David has responded. So I should warn people in the audience, and you, Stephen, as well. There is a sort of 20 to 30 second delay. So David has replied to the previous point you made, which is that's right. I never claim that it's the main cause of non-replication, just a cause. I just want to move, if I may, to a couple of questions. One from Dorothy Bishop, and also another from Nick Holmes, which touch on the same thing. And I'm interested in this as well, which is, so from Nick Holmes, we have this variation of the question, which is, can you please say a bit more about why the standard error of typical studies are too low in your view? And Dorothy asks, could you please say more about why standard errors are often wrong? So yeah, could you elaborate?
Okay, so in my field, if I ran a clinical trial, I could run a cluster randomized trial. What I could do is I could allocate all of the patients in one center to one treatment and another center to another treatment. Of course, I'd need lots of centers to make this work, but a cluster randomized trial is a perfectly acceptable thing to do. Now, of course, what I need to do is I need to calculate the standard error quite differently if I run a cluster randomized trial to a parallel group trial. When we run clinical trials, this is absolutely clear. It's absolutely clear from the randomization procedure which you're doing. But now, supposing that what I had was I had a cluster randomized trial and I actually fitted a number of covariates. So I fit the covariates to deal with the fact that there might be possibly some differences between centers. The FDA still would not allow me to use the standard error formula for a parallel group study. They would still expect me to use the between study variation as a way of driving the standard error. But now imagine you have an observational study. Basically, the data fell off the back of a lorry. You got these data, you don't really have any control as to how they came. So what you're now going to do is you're going to fit a number of predictors. But once you've fitted the predictors, you will then assume that the standard error decreases according to the square root of n, where n is the number of subjects. And as a trialist, I say, why? Why should it reduce according to the number of subjects? Clinical trials don't in general reduce according to the number of subjects. Only one sort does, and that's the parallel group trial. Why do you assume that these data that fell off the back of a lorry can somehow be made equivalent just by fitting a few covariates to the parallel group study, supposing in fact that they're more like the cluster randomized study? Then in that case, you might find, and in fact, David Cox has drawn attention to this, you might find that the standard error is reduced something like the according to the fourth root of n rather than the square root of n. So it's hardly surprising that there are a number of studies that are not randomized clinical trials that don't replicate very well. And my explanation is the standard errors that are being quoted are implausibly low.
Wonderful, thank you, Stephen. Nick and Dorothy, please do feel free to reply with any more clarifying comments or questions you might have, because there will be a slight delay in them hearing what you've said. What I would just like to ask you to do, Stephen, is if you could you perhaps return to a previous slide which you had, which was the kind of the crux, the central story that you're trying to get across, the coherence slide, which is just several slides back, where you were talking about sort of the largest experiment possible and defining what is sort of replication or at least the target of what we are trying to achieve with replication. Yeah, so if you just make that large again, perfect, thank you. So Ian asked a question, which is he'd like to know how you would actually do a reproducibility experiment using this sort of infinitely large experiment.
Well, I mean, you can't do that, but what I'm just pointing out is you should be careful if what you imagine is that somehow a particular study that is of moderate size can of itself be regarded as being adequate for judging how true a particular result is. I mean, what happens in drug development is that you gradually go up to larger studies. So you start with fairly small ones and your studies get larger. And that's how you judge as to whether your previous round of things are reasonable. In many cases, you're just going to have to accept that you don't know. That's fine.
Interesting.
But the whole business of somehow assuming that the meaning of a p-value is the p-value to follow is an even worse interpretation, I think, than the common misinterpretation of p-value. And all I was also doing with this particular diagram is where I did the same thing in a Bayesian framework. It doesn't matter what statistic you use, unless you have some other information apart from the statistic itself, information in the form of a formative prior, then in that case, it simply is unreasonable to expect that the second time you look at it, the result on its own will be even more impressive. And as a similar mistake is made by people, you know, who say regarding meta-analysis that, well, if only I had more studies, the result would be significant. Basically, you are where you are. That's where you are once you've completed a particular study. You know, whatever you choose to express the particular uncertainty, a posterior Bayesian distribution, I've got no problem against that, provided you make clear what prior you've used. That is your prediction for where you are, for what you know about the world. It's not a prediction for what will happen for the next experiment. That's something else you need to do. And in fact, although Bayesians seem to be very keen on predictive distributions, there are some occasions where the predictive distribution itself is a misleading way to look at things.
Okay, thank you, Stephen. A couple of things. So just going back on the point regarding the standard errors, Dorothy asks that it would be great if you have a reference to the arguments on standard error.
Yeah, sure. I can do that. I don't know what the best way to do that is.
Well, what we can do is, because we will eventually upload your slides to our OSF page, which will be publicly available, we can just upload PDFs or a list of references that you recommend.
So we have a paper together with some colleagues at the Luxembourg Institute of Health, where I used to be. We did some work on historical studies. And in fact, we're not the first person to do this. There's been some brilliant work coming out of Novartis, who've done a lot of interesting methodological work on historical studies. And the basic thing you find is that the between study variation in, let's say, the placebo rate is particularly important. By the way, I can demonstrate this with the COVID trials quite easily. If you look at the various COVID trials, you'll find that the placebo infection rates are all over the place. But provided you use concurrent control, that doesn't matter. But if you're going to use historical data, the hidden components of variation that many people ignore is the variation between studies. And in some particular consultancy work that we did, we were able to show that 1,400 historical patients were about equivalent to 50 concurrent controls. That was all the information you had, simply because the variation between studies was so large. And of course, if you, even then, you're making the implicit assumption that the historical studies are somehow exchangeable with the current one. You're just allowing for the fact that there's a huge study-to-study variation. But it's this study-to-study variation that people overlook. And concurrent control is what allows us to come to such precise conclusions in clinical trials. And when we don't have it, and that includes for many observational studies, we should be very, very cautious about what we claim.
Thank you, Stephen. Yes, so.
But I have a paper, Olivier Collignon, who used to be at the EMA, is the lead author on this, and he's done some further good work on this. I will send through the references to that.
Wonderful, thank you, Stephen. Yes, we'll circulate that along with the video and everything, or the other materials. So we've got another reply from David. So he says, in my single channel days, the variance between replicate estimates was always bigger than the internal estimates of error based on covariance matrix from Hessian. They agree fine with simulated data, so I can only assume that there are systematic differences between replicate experiments.
Yeah, I think that's true. But I think there are two different, I mean, thinking of it with my statistical hat, there are two different things to watch out for. One is the main effect of study. This can be dealt with quite well in the field in which I work by having concurrent control. And I think that the vaccine studies for COVID have done very well in this particular way, as far as I can judge. I think they have convincingly done well with having the concurrent placebo controls. That's the main effect of study. More difficult is if you have a study by treatment interaction. So it could be, for example, that the vaccines work not as well in different populations. That, of course, is a more unpleasant problem in a way. But concurrent control deals with the first one.
Wonderful. Just to warn everybody, we know we scheduled this talk to finish at 2, but Stephen has graciously allowed sort of 15 minutes sort of grace for anybody who wants to hang on and ask any more last questions. What I was going to ask Stephen actually is to move this away more to the sort of broader concerns in the sort of open science reproducibility bubble, however you like, because the sort of questions that come to mind, which are proposed actually by Ian, which is, you know, if p-values are not the cause, what are issues, or do you think there's not a crisis at all, or are there other issues that have led to this crisis? do you think that all we're looking at really is just normal variation rather than a genuine replication crisis? I wonder whether you could just comment on those kind of broader concerns that people generally have, or their immediate response when they see sort of that their study doesn't replicate.
Well, first of all, let me just get back to the standard error thing briefly. So basically what I'm saying is that people imagine that the villain in the piece is something to do with the prior distribution. So effectively, as I showed in my talk, there's a historical connection between p-values and the uninformative prior. So if you regard p-values as being a problem, you might as well say the uninformative prior distribution is a problem. And I don't necessarily quarrel with that. And that the way to fix this is by somehow having a more informative prior. But for me, that's only half the story. The posterior distribution is also made up of the statistic and its standard error. And people have been worrying about the prior precision, but they should also be worrying about the data precision. The data precision is not what it seems to be for many, many reasons. And for me, this is plausibly the villain in the piece in many cases. It's the villain in the piece because people are cheating the way in which they do things. And there've been a number of, I've already given some arguments as to why I think observational studies have quota standard errors are too small, but there are other things. The file draw problem, of course, which people have drawn attention to, that people don't tend to hide negative studies. That causes a problem. But there are also other problems in that the file draw problem exists within studies. And for example, the Tripod Initiative has tried to get people to be honest regarding bioinformatic type approaches to prognostic studies, where essentially people publish a paper in which they claim that they searched over something like 20 models, but in actual fact, if you look more deeply, they searched over 2,000 and chose the one that fitted best. And so a massive overfitting is going on there. And so those are problems. Then of course, people, there's also the sociological dimension that people have pointed out, that the essentially the motivation in academic circles is wrong. Positive studies are rewarded and negative studies aren't, and publication matters and so forth. So these are also problems. Ironically, I think that drug development is one area where, in fact, things are policed very, very formally, although, of course, as soon as that formal straitjacket is escaped, particularly thinking of post-marketing studies and things like that, then there is a problem. But actually, having to pre-register your studies is maybe one particular approach which helps. And there is a movement, I know, among psychologists to do this, and I think that's an interesting initiative. I mean, I don't know whether that answers the question or not. I'm not absolutely certain what you're looking for there.
Yes, it was a nebulous one. I admit it was more. I mean, you've answered it, I think, throughout the talk. I think it's more. I think what I found interesting, the way that you started the talk, was your starting point was that sort of there's lots of questionable findings in sort of social science research, and then you were surprised to find that some of those are robust, where I think most people, as you've said, come from a different viewpoint, which is they assume that they're solid and then they're surprised when they're not. And if we ignore the p-values issue and Bayes, do you think there is a sort of base rate, I guess, of variation in findings? And I think do you think that people are being too excited and interpreting this as a replication crisis, whereas really we're just seeing just noise? That's what you would expect.
It could be. I mean, I think I certainly like the quote I ended with, Gigerenzer and Revsky. I think we need many ways of looking at data, because partly if they disagree with each other, it's a sort of encouragement to try and find more evidence or to think about it differently or to try and resolve an apparent contradiction. I think that can be valuable. And so I think that just having one system is not necessarily a good thing. This will offend all purists, but I think that's the case. So I think that that's one particular thing that we can do. We can't always require completely convincing evidence, and the COVID crisis has really shown us that this is the case. Having said that, there have been some very poor work, some very shoddy clinical trial work, unfortunately, but also some excellent work on the whole. The vaccine trials, I think, have been very, very well done. And I'm proud of the work the statisticians have done on them, although I have to admit that in the end, the most important work was finding vaccines that worked, not proving that they worked. But nevertheless, the work on proving that they worked was very impressive, and maybe we can learn something from that as well. I think there are a lot of interesting things we could do. I think I'm hoping that I can try and succeed in contacting all the 5 major companies that have produced convincing results for vaccines and persuade them to pool the data between themselves to see if they can explain the difference in placebo infection rates per trial. If they can't, then this highlights the problem that observational studies will have. Note, I'm not claiming that variation in placebo infection rates is a problem because these trials practice concurrent control. It would be a problem if they hadn't.
Wonderful. Thank you, Stephen. I think that's quite a nice point to end on. We don't have any other residual questions in the Q&A. Just a few announcements before we sign off. A few talks that might help supplement this talk. One last week was hosted by the RIOT Science Club at Rotterdam, where we were joined by EJ Wagermakers. Actually, that was on the 3rd, earlier this week. And we also have Jill Jacobson, who gave a talk on how do we evaluate replication, what does it mean, and the various different ways to define a successful replication. Thank you very much, Stephen, for a really, really engaging and thought-provoking talk. It was a very novel, at least from my sort of open science bubble viewpoint, way of looking at things, and it was a really nice Q&A session as well. Thank you again for your time, and to everybody, we'll circulate the recording as soon as possible, along with the sort of supplementary materials and the slides. Thank you very much, Stephen. I'm just going to finish the stream, but you can stay on the call and we can just quickly debrief. See you all next time.
Okay. Yeah, thanks so much for the invitation, and thanks for the questions, everybody.